Okay, welcome everyone back to the Associated Research webinar series. This is our first webinar of 2017, so we appreciate you attending this one, and if you attended the ones in the past. If you're new to our webinar series, how we work is today we'll start with Electrical Safety Testing 101, and we progressively build on our webinars, the technical information, pretty much ending at like a complete medical testing, line leakage, applied part, pretty much the toughest, most intricate type of electrical safety testing there is. But today, we're going to begin with Electrical Safety Testing 101. Before I begin, let's introduce our team here. My name is Anthony. I will be your presenter. I'm an applications engineer here with Associated Research. We have Bashan, who is also the applications engineer on our team. So he got promoted, applications leader. Congrats, Bashan. And then we have Allison, who is our organizer, marketing coordinator. So if you have any issues or questions concerning the material being presented, please use our Q&A utility. So Bashan is on the line, and he's ready to answer any questions, whether it be related to testing our instruments or any information that I present in this slide. This webinar is being recorded, as all of our webinars are. You can view the same webinar but last year's version on YouTube or through our website. Please contact Allison Oba if you want a copy of this presentation. There's her email. Let's see. So let's get right into it. What are our learning objectives for this webinar? So we're going to talk about safety, testing, and at the end provide some testing resources. We'll begin with some potential shock hazards, and then how to set up a safe workstation, or what makes a workstation safe. And then we'll get into why test and talk specifically about pretty much the main characteristics of what separates class 1 versus class 2, right? Depending on which you're testing, that's what dictates the type of parameters or voltage that you'll be testing to per the standard. So our presentation objectives are to recognize an electrical safety hazard, we'll set up a safe workstation, and we'll provide you with some resources for operator training. Okay, so in the past, we would show you a couple pictures of, two pictures of, someone getting shocked by making contact with a live part, and, that current flowing through the body to ground, and then someone making contact with 2 points, and that current flowing through their chest, in one arm out the other. But this we want to give you a little bit more detail of what's happening in those scenarios. So let's go through these various circuits and kind of talk about what's going on. So we kind of all know how does a bird land on a power line and not get shocked? Well, they are now at high potential, right? They're at high potential, but because they're not standing on ground like most people are, there's no danger there because they're just an open circuit, right? They're an open wire hanging off the high side of the voltage, and there's just no path for current to return to the source or return to ground. Now, we have our operator here who's also not being shocked, although he is standing on the ground, but that's because he's in contact with the low side of voltage, right? You can tell this source, whatever this power source is, whether it be a power source that you buy, from APT, or whether it be a power line, right? That he's in contact with the low side, which is reference to Earth. So in essence, there's no potential difference across him, right? Both points are at 0 volts. So there's just no electric field there. There's no voltage to drive current through him. Contact with the low side of voltage places operator at same potential as ground. Therefore, there's no potential difference or voltage to allow current to flow through him. So that's one of the benefits of having your source grounded, right? You're kind of guaranteed to have one side of it safe. One side where if contact's made, you're not going to experience any shock. Now, the circumstances become different when he comes into contact with the high side of voltage. Again, the bird, same place, right? He is, or it is an open circuit, right? There's no path for current to flow through the bird, but now our operator is in contact with the high side of voltage. So what's that mean? That means his hand is at, what 120 volts or 1,000 volts, whatever it is, and his foot is at 0 volts. So he directly has voltage applied across his body, and so his body becomes a wire for that current to flow through him and return to ground. So that's why it's kind of important to mark, to understand what your lines and your neutrals are, to identify them, to understand what the black wire and the white wire means. For the most part, your black wire or red wire is line, or the high side or the hot side. There's a lot of terms to describe that, and for the most part, your white is your neutral. Now that doesn't always mean that white is safe, right? You can have it doesn't mean that it's referenced to Earth all the time. So it's important to find out what type of source you have. Is it referenced to Earth? Is it a split phase where you have two hots coming in? So in that case, you're at danger at any side of the voltage. So to elaborate here, right, we see the current flowing through the high side, through his body, and now it's returning to the source through Earth. Path for current through the dirt. Let's look at a couple different scenarios. So now there's something a little bit different about these sources. You can see, we'll go back to the previous picture. You can see here we have referenced this source to Earth as opposed to, or grounded it, or grounded neutral. There's, again, lots of different terms for that. But here we have what's called an isolated power source, right? There's different grades of isolation. I think the highest would be a medical grade, which theoretically ensures that there's no way anyone can get shocked when coming into contact with it, because through ground there is no source for that current to return to that isolated transformer where that current is coming from, right? So between the wall where you're plugging into and the transformer which is outputting, there's isolation there, right? Now, ideally that's strong enough to, it's strong enough where it's a strong isolation between your one side that's outputting and your input side. So your output and your input side. And it's that insulation that stops that current from returning through ground. Again, with this guy, he can contact either side, right? The high side or the low side. Since the low side of the transformer is not referenced to ground, making contact with any point of the circuit while standing on ground does not allow current a path back to the source. Now, these aren't 100% dummy proof, right? Because the danger with an ungrounded power source, or a source not referenced to Earth, is the possibility of an accidental grounding or a contact made with 2 points of the circuit. So if this was a power line, what would happen if a tree branch were to grow and come into contact with one side of these lines? Well, now you've just grounded it, right? That tree branch is just a wire. That tree is just a wire which is connected to Earth. And so now you've just referenced that source to Earth. Or in the case we have here, we have two operators who are both standing on ground and are coming into contact with this circuit. And so what did you just do, right? You just shorted this resistor here, and now current is taking the path through an operator into the ground, coming out of the ground into the second operator and back to the source. So again, an isolated, especially a medical grade isolated transformer or source, power source, is theoretically, as safe as it can be, but there's other ways or circumstances that can cause it to become referenced to Earth, right? If there's studs in the back, if it comes into contact with some sort of cart or metal object, you've now referenced it potentially to Earth, and it's become the type of source we spoke to previously, where if you come into contact with the high side, you will get shocked. So I hope the big takeaway from this is, regardless of the type of power source you have, there's always a potential for shock, and so that's why it's important to take extra measures in the form of PPE and other sorts that we'll discuss further. Another danger that a lot of people aren't familiar with is capacitors, right? Or maybe not even a capacitor, but something that has a capacitive characteristic to it, right? If I'm a wire manufacturer, well, let's discuss what a capacitor is first, right? It consists of two conducting surfaces separated by a dielectric, which is another word for an insulator. So the effect of this is that when a voltage is applied, charge flows into the capacitor and is stored, right? So once you remove the power from a capacitor, that storage is, that charge is still there, right? Stored. When an external circuit is connected to the capacitor, this stored charge will flow from the capacitor into the circuit, and that circuit could be someone just coming into contact with it. So I kind of call these unintended capacitors, which can cause potential shock hazards. So what's a cap is as simple as two metal plates, right, separated by an insulator. And so a cable manufacturer, these spools of cable, what do you have here? You have a bunch of metal separated by that insulator, right? So it's a huge capacitor, or it develops a capacitive characteristic. And so when our customers are high-potting these long spools of wire, they may not be taking the proper steps to discharge this spool. And so, the first person to come into contact with it, or we're told stories of, the forklift operator who picks these up, well, they're always getting dinged, or they're always getting shocked, because you've just charged this huge capacitor and didn't take the proper steps to discharge it. And so I'm sure the next question is like, well, what are the proper steps to discharge it, right? So you need to realize, so how does a capacitor work, right? If I go to 1,000 volts, I've just charged my cap to 1,000 volts, right? But now if you if you use the ramp down feature that come with our high-pot testers, well, that ramp down feature is theoretically, now I'm charging it to 800 volts, 600 volts, 5, 4, 3, 2, 1, to the point where now you just completely discharge that DUT. So I know in the production line, it's all about testing them as fast as possible, but if you have these type of DUTs that come with a capacitive characteristic, it's useful or beneficial safety-wise to add a ramp down feature. Or another thing is what's called a hot stick, or it's a discharging stick, where you just kind of short out the cap, and now you've just discharged that charge through that charging stick to ground. So it's usually got a metal piece that's a wire that goes directly to ground. And so now you've just let that current go directly to ground, and now you're fine. You've discharged your DUT. So those are a few of the steps you could take to make sure you don't have these charged, heating elements or motors or spools of wires sitting around your warehouse, where they can become hazardous situations. So now that we understand how we get shocked, let's kind of understand the effects of electrical current through the human body. Now, these numbers aren't, written in stone. They vary, depending on where you go. But for the most part, they ring pretty true, right? So to perceive shock at about 0.5 milliamp to 1 milliamp, that's when you'll start feeling a tingle or a buzz, where there's no pain involved, but you understand something's happening. Even when you're touching your high-pot tester, perhaps, or picking it up, you might feel like it feels like it's vibrating, but that could just be stray leakage current that you're feeling where it's not high enough to hurt you or feel a sensation of pain, but there's this, it's hard to describe, right? But it feels like a vibration or a tingle. At about 5 milliamps, we'll feel a slight shock or a startled reaction. Um, at 6 to 30 milliamps, now you start feeling a painful shock and the inability to let go, right? You can no longer control your motor skills. So above that, now you're, depending on the duration, now we're getting to the range where death is possible and severe burns. And once you're in the 10 amps, I mean, once you're in that range, you'd be pretty lucky to walk away from that. So the effects of current can vary drastically due to a number of variables, which we'll discuss. But it's important to be mindful to the shock hazards to which you could be exposed. For example, the 3705 hypot tester has the capability to output 20 milliamps. So at 20 milliamps here, we're already at painful shock and ability to let go. And, that is enough actually to get you to, ventricular fibrillation. So it's important to take the proper steps to make sure you've created a safe workstation so this isn't a scenario your operators come into contact with. Let's go to the next slide. I was at a trivia night and fibrillation was how to spell fibrillation and I got it wrong. I just want to let everyone know that. So let's talk about the severity of electrical shock and what factors determine how severe the injury will be. So there's physical condition and response, right? If someone already has a heart condition or their response, right? What did that shock make them do? Were they on a ladder? Obviously that's going to lead to more serious injuries. The path of the electrical current through the body. In one of our previous pictures, that's no longer on this webinar, but we have an operator touching a live part and with both hands, and so now that path is going through his chest cavity, through his heart. If something's coming in one arm and maybe out of your elbow, well, while you can get major burns, it's less dangerous than something passing through your heart, right? Because now that once you start messing with the beating tendency or how your heart beats, right? It's hard to get it back on track. So there's the path in which the current takes determines the severity of the shock. Obviously the duration, length of time the person exposed, the longer, the worse it'll be in the magnitude, right? If I'm exposed to 10 volts versus 100 volts versus 1,000 volts, then we know I'm going to have more current flowing through me. And also the frequency, right? At higher frequencies, I would expect worse injuries. And so via OSHA, they actually call out 4 main types of electrical injuries. One being electrocution, which is fatal. I think a lot of people misuse that word. I'm sure I know I have in the past. I electrocuted myself. That's not true. Electric shock, which is the most common, right? We all feel a ding and we let go, and while it hurt momentarily, we all end up, for the most part, people can survive that. Then there's burns, where that's something more where you have that inability to let go, and that current is flowing through that wire, which happens to be you, right? For a long time, and just like that's why we ground bond test, right? Let's inject a large amount of current into this wire and see if it holds, or will it burn up? Well, our bodies and our nervous system does the same thing. Our blood vessels, they do the same thing, right? Perhaps they can carry that current for a while, but the longer that is, the more likelihood that we will get burned. And then falls caused as a result of contact with electrical energy, right? So that same guy who was on a ladder, or someone in a confined space, or someone who gets shocked who has other live parts behind them, right? If they get pushed into that, well, that is going to increase the severity of their electrical shock. So let's talk about our human body. Like I just said, we're just a big wire, right? That hopefully never gets current passed through it. Well, I mean, we're constantly have pulses passing through us, right? So we can move our arms and our body and everything. But those are low level where um, our body is really just a huge resistor, right? For the most part, I think you can consider the human body a 1 kilo ohm resistor. On average, we have about 1,000 to 1,500 ohms of resistance. The outer layer of the skin provides the largest percentage of the body's electrical resistance, right? Our skin is our insulator, right? Ideally, our skin can stop um, low volt current that comes from low voltage from penetrating our skin. But once that skin is punctured, now there's not much resistance to that current flowing through us. The part of the body which conducts electricity the best are blood vessels and nerves, right? Our nervous system, which makes sense. So let's think about that, right? If we're a 1K ohm resistor, and I come into contact with a wall outlet, well, the current required to light a simple 7-watt 120 volt lamp passes across the chest is enough to cause fatality, because if we do the math, 120 divided by 1K, well, now we are at 120 milliamps. And if we go back to that table, 120 milliamps, well, extremely painful, respiratory arrest, ventricular fibrillation, and death is possible. So that's just kind of to give you general insight, right? Just general understanding of how much danger there is behind that wall outlet. And it has a lot to do with our human body and its impedance. And so if we look at this guy, technically the current could flow to the light bulb, but it's also going to probably go through his body as well, right? Since he's grounded, depending on the path of least resistance, the current might split up, light the light bulb, and go through his leg. So again, we're just trying to emphasize the importance of taking the proper steps to make sure you have a safe workstation. To be exposed to line voltage doesn't mean just sticking your finger in an outlet, right? I mean, we have line voltage throughout our workstations, and it's important to identify them and, again, take the proper steps to alleviate any hazard. So now that we understand how we get shocked, why we get shocked, and what happens to us when we get shocked, let's talk about that's technically the main reason of why we test, right? Because we want to make sure people don't get shocked with our products. So these are the 4 main reasons why you should safety test your product prior to shipment. So I think safety is the most important one, right? We want to ensure that the product we're shipping out is not going to pose a hazard to the end user. That's why most people do a quick high pot or ground bound 1-second test right before it goes in the box ready to ship. Quality. You want to be able to detect workmanship defects and prevent faulty components from being installed, right? A lot of people are told to only run an AC, their high pot test. They might do AC and DC. They might do at a higher voltage. They might run longer tests because they just want the quality of their products, not to just meet the minimum of UL standards, but to go above that. So a lot of companies have internal standards, right? Internal quality standards where I understand that the IEC or UL or TUV is telling me that this is what I have to do, but that's the minimum. That's the minimum I have to do. Some companies want to take the onus of saying, well, I want it to be better than that. And that's where you develop quality in products, right? Cost control. You identify production problems before a product is shipped, right? If you don't want, this is more for type testing, right? You don't want to say, hey, I have a finished product, start development, and then realize I have faulty insulation or lower quality ground circuit. So that prevents costly recalls. And this one's probably just as important as all the other ones. Prevent product liability suits because the responsibility of performing electrical safety tests ultimately rests on the manufacturer, right? Your NRTL is just telling you what you need to do, what you have to do. Um, but once it comes to production, you will get audits here and there, but at the end of the day, you know, you are responsible to make sure your products are leaving your factory safe. Um, so I think so. Let's talk about the testing laboratories. Let's These are obviously the most common: Underwriter Laboratories, TUV, uh, the Canadian Standards Association, ETL, which is a growing testing laboratory, um, and then we have the China compulsory certification. So depending where you want to sell, um, that kind of dictates who you should be testing with. Now, most labs will say, our testing will make you compliant with, the CCC or CSA, but you just might have to pay more to run different types of tests. So with that, we wanted to ask a poll question. I guess just in general, we want to know, what's the frequency, no pun intended, of people getting shocked at the workplace. So has your company had an employee incident involving electric shock in the past year? So Allison will open up this poll, and we can talk about the results. And it's also good for you to just kind of understand what other companies see, right? Another thing is there's a stigma. I know, when I was a college student, I was an intern at a lab, and I was testing a strobe light which had two inputs, one to power the strobe and one to send signals to the strobe. And it was my first week as an intern, and I turned off the source which was sending the signals, but I didn't turn off the source which was just powering the thing on. And so I grabbed it and got shocked, and my hand was in so much pain. But the first thing I thought was like, oh my God, I hope no one saw me. Looking around, make sure no one, um, you know, the technicians can't wait to put the engineering student in this place, right? When they get shocked. But so the stigma is like, don't report it, don't say anything, and that's kind of something that that's probably not how it should be. It's important to report that not so someone gets in trouble, but that I've just learned how a shock can happen. Maybe I need to implement new training, and the next intern will know how a strobe works, or will know, hey, make sure you power both sources off. So I think Allison can spit out our results here.
Hi, Anthony, and thank you everybody for participating in our poll today. Has your company had an employee incident involving electric shock in the past year? 29% of people reported that yes, they have had an incident of electric shock in the last year. 43% of people say no, that they have not, and 29% of people say they aren't sure. Thank you all for participating.
Okay, so that means about, generalizing, like a third of companies, right, still have this going on. And I know this webinar, let me close this, sorry about that. So, we're not getting too technical into the type of tests. That's kind of what our next webinar is, EST, Electrical Safety Testing 102. What is a high pot test? What's the physics behind it, right? What's a ground bond test? What is ground continuity? What is line leakage? What is an insulation resistance test? And what's actually happened. But before we get you to testing, we want you to just kind of recognize the hazards of testing. So that's the takeaway of this first webinar. But as we move forward, we'll progress into more technical information. Speaking of technical information, so here's something that standards abide by, right, or are separated by these two different types of classes. NRTLs, which stand for Nationally Recognized Testing Laboratories. So their standards dictate that electrical products incorporate two lines of defense to protect the user from electrical shock. So what's the first line of defense that every product has? That's insulation, right? That's separates power lines from low voltage circuits, right? So that's the input power from the rest of the circuits in your product, which are doing different things at different voltages, which usually could be air, right? A lot of standards will say, hey, this many centimeters need to be between these two boards. Um, Insulation also separates power lines from isolated power supplies, right? So what we spoke to earlier, the input power versus what's outputting, right? If you have an isolated power source, there's a level of insulation. If it's medical grade, then it's a lot higher and a lot safer. It also isolates input power from the chassis or case of an electrical device. So again, that can be my laptop here in front of me has a plastic cover that's insulating me from the electrically charged boards on the inside, right? Um, Now, the second layer of defense that some products have is the safety ground. It allows dangerous fault current to return to the system ground. So what's that mean, right? That means any current that falls off that line neutral circuit and falls off those low voltage circuits, well, it wants to go somewhere. And so luckily we have a highly conductive, really low resistance path for it to go on, and that's our ground, right? So our ground catches all that current and returns it to Earth, where if that wasn't there, that insulation will be tested, and if that insulation fails, well, now someone can come into contact with it and get shocked. It enables circuit breakers to open. Um, it safeguards against fire, right, and protects against damage to electrical equipment. Um, so those are the two types of insulation, right? Now, talking specifically about Class 1 products, well, Class 1 products, those are your three-prong products. Okay, it's kind of, you can easily remember it. Class 2 has two prongs, so the other one must be the three-prong. Right, Class 1 products terminate in three-prong line cord, a line neutral and a ground. The ground prong connects to the product chassis, and safety through basic insulation and proper grounding, right? So those are the two lines of defense. Basic insulation and then proper grounding. So now we have Class 2 product, which its two lines of defense are double insulated products, right? So it's twice. I don't know if it's exactly twice the insulation of a Class 1 product, but it's stronger two-layer insulation. This terminates in a two-line cord, so it just has a line of neutral, right? Can you break off that ground prong from a Class 1 product, and will it still work? Of course. Then it's just a Class 2 product, except you don't have double insulation and you've just lost one of your lines of defense. And so the safety comes, as I said earlier, through the dual layer of insulation. And, again, if you're combing through standards, there'll be different tables. Different tables will say, hey, if you're a Class 1 product, these are the voltage levels you need to test at. And in that table will say no more than this much current can be seen when doing your dielectric withstand test. But for the most part, you'll see no breakdown shall occur, right? And so, but what does that mean? No, there's no definition of breakdown in standards, but so the onus fell on the hypot testing companies to identify what a breakdown is, right? And so a breakdown is pretty much when our instruments pretty much see a short through your insulation, right? Once there is a short through your insulation, well, I know there's definitely an issue with your insulation, a huge hole. Somehow, current is now shorted back to the return, and so my transformer inside my hypot tester, which can usually only do 10, 20, 30 milliamps, well, now this short is asking for way more current than my transformer can provide, and so then it gets put in this state of overpower protection, right? I need to protect myself because someone has just shorted my output and is asking for way more current than I can provide. And so when we see that OPP, failure or that OPP protection activated, well, that's one of the ways we say, okay, well, breakdown has occurred. Um, so that's a little insight into how our breakdown is defined. Okay, let's talk about electrical accidents in the workplace. Most electrical accidents in the workplace are a direct result of one of the following three factors. Unsafe equipment or installation, right? Unsafe equipment, so that means are you calibrating it? Is it exposed to an atmosphere where there's lots of dust, or it's just not being um, installed in a safe manner? An unsafe environment, are there constantly, people walking by that shouldn't be? OSHA calls out for certain distances for unqualified people. They shouldn't be approaching any high voltage instruments or sources if they're not trained to operate on them. And unsafe work practices, that kind of um, alludes to what I just said, right? Are people not wearing their proper protection? It's one thing for a company to invest in PPE, personal protective equipment, but if your operators are now cutting corners and not wearing their gloves or aren't plugging in the tower light, which lets you know if it's safe or not safe. Those would be considered unsafe work practices. So these accidents can be prevented through the use of insulation, guarding, grounding, electrical protective devices, and safe work practices. So let's get into how you would create a safe work area. Operator training, right? Operator training is probably one of the most important things because uh, you don't want your operators to just memorize what this high-pod instrument is doing, right? Like you want them to understand what's actually happening. Like what's the purpose of this test? I remember, again, as an intern in a lab, I used high-pod instruments and I would run high-pod tests, but I kind of just memorized a procedure. I didn't quite understand until I came to associate research, what was actually happening, how was I testing this installation, what a green light and a red light meant. So operator training is important, right? Understanding voltage and current and identifying potential shock hazards. Utilizing safety devices. So if you can't guarantee that training will be retained, right? So you need to kind of have some redundancies built into your test system by utilizing safety devices, a DUT enclosure, signal tower lights, insulation mats, etc. At the end of the day, it's the responsibility of the employer to ensure safe working conditions and safe working environments for all test operators. So let's talk specifically about these PPE products. So what's an enclosure? What's a DUT enclosure, right? We sell these. They're an enclosure designed to remove shock hazards. So how does it do that? Well, this enclosure is directly connected to our interlock. Our interlock is there to open the output relay or close the output relay. It's like a key to your car. It's not going to start if that key's not in there. And so whenever this door opens, I just pulled the key out of my high-pod tester, so there's no way it's going to output. And so that's kind of a way to dummy-proof your testing station, right? If an operator needs to put a new sample in, well, he needs to open the door, right? Well, if the door's open, there's no chance of him getting shocked. Only when the door is closed will that high-pod tester be able to output. And so that's kind of a very popular and almost dummy-proof. Someone would almost have to want to be trying to get shocked if they're shocked and you have a DUT enclosure on your test system. Cabling and insulation. So it's important that you're not just buying random accessories, right? These are rated to handle the outputs of the instruments they come with. And so, it states on the actual cables, or it should, what is that cable rated for? A lot of our instruments that test up to 20 kV, well, those leads are tested up to are rated up to 30 or 40 kV. Our 5 kV instruments, well, that's again, the insulation on those leads goes up to 30 kV. So it's important. You've just invested a lot of money into this high pot tester to verify that your products are safe and sell these products and turn a profit. Well, it's important to also recognize your accessories and your leads. Those are a huge part of your testing system. PPE, personal protective equipment, high voltage gloves. So they have shoes that are specifically made with materials that will isolate you from ground. Now we all know, like, well, my shoes are already made out of rubber or what have you, but that doesn't. Sure, that does provide some insulation, but it's not enough to stop current from returning to ground. Um, and then just something as simple as a high voltage sign. Train your employees. If there's a high voltage sign there, you're not supposed to be there. Turn around or make sure you are escorted by someone who's trained. Um, so methods of safety testing station with positive protection. So OSHA considers someone who uses a DUT enclosure to have positive protection for the reasons I stated earlier, right? It's dummy proof. Someone almost is trying to get shocked if they're shocked with a DUT enclosure. Also, OSHA regular says that if the employer does not consider the employee trained or qualified to handle those high voltage instruments, then there needs to be a 10-foot barrier where they don't get near that instrument. Now, it's you who decides who's qualified or not. So again, the onus falls on the manufacturer to identify or to label someone as qualified or not qualified. And again, we see our e-stop, which is an emergency stop, right? If someone's getting shocked, someone can run over there and turn it off. If there's some sort of wire comes loose, well, you can hit that e-stop to, mitigate that hazardous situation. And a high voltage sign to let someone, visitors know, or someone passing through on a tour. This is a high voltage area. If you're not, just the fact that you're letting someone know that this is a dangerous area is also essential. Now, sometimes a DUT enclosure can't be used, right? This guy's testing a washer or a dryer. We've seen some companies that build their own DUT enclosures, and these are very reputable medical device manufacturers where they'll have a huge gate that closes and controls the interlock. But something like that isn't mandatory, right? It's not necessary. You can cage off or gate off, a 10-foot area where unqualified people can't enter. You can see our operator here is also standing on an isolation mat, right? It's a level of insulation like the shoes I spoke of earlier where you are isolated from ground. And again, we still have our tower light, we have our e-stop switch, and our high voltage signs. I think this is a pretty cool device, right? It's our DPR, dual palm remote switch. So that means your operator, if your operator is getting shocked, it usually has to do with their arms or hands being somewhere where it shouldn't be. And so this is also this PPE device controls our interlock, right? If those two buttons are not being pressed, well, the interlock is open and there will be no output from your instrument. Only when both of them are pressed within half a second will that output relay be closed and will a test be sent a start signal. And it has to be within half a second. So if someone's trying to just use one hand, and obviously these DPRs are spread apart far enough where someone can't activate it just with one arm, or in any type of irresponsible way. Um, Here we have our signal tower light. It illuminates red when a test is active, right? So red means stop, don't walk by, or you're not allowed in this area. Um, and green means, well, it means you've passed your test, but it also means I'm not outputting anymore. So green light, you can go, you can walk through here. Um, Again, these type of rules is kind of for the employer to identify and to label and to set up your own type of system on how to make your workstation safe. So again, mounted light warns operator in the nearby area to the status of the HiPot test and if the instrument is outputting high voltage. And the higher the better, the more plain sight area the better. And it's important to note you need to be able to power this guy up, right? This tower light takes 120 volts, and so you need to mount this to somewhere where you can give it its input power. The HiPot instrument will give it its signals, hey, turn red or green through the signal output, through PLC signals, but it's important to note, like, it needs to be near somewhere where you can provide input power. Again, in our pictures previously, we saw these insulation mats, right? The mat isolates the operator from ground while testing, which greatly mitigates the shock hazard, right? You become an open circuit when you're standing on this. There is no path for current to flow through when you're on this mat. When you take one step off of it, well, now you're kind of a completed circuit to ground waiting for current to flow through you. And so we've seen, a lot of going on visits to manufacturers where, not entirely the whole floor, but where there is high voltage testing, that area the floor will be purely just squares of insulation mats. So here is our second poll question. So I think, what safeguards are you currently using in your workstation? And so Allison will open that up. And, I think this feedback is just important for, if I was attending on the other side, I'd want to see, what, not necessarily competitors, but, other companies, what do they think are the best options to protect their workstation? Are they just using, how many went all the way and got positive protection and are using a DUT enclosure, and how many are actually using insulation mats, or just what they're using compared to what you're using. So we'll let Allison open that poll and she can give us the results. I believe on our website we also have kits, PPE kits, where price-wise I'm not sure, but you can buy the insulation mat with a sign, with a tower light. You can see all that at www.arisafety.com.
Hi everyone, thank you for participating in our poll. It's great to see that a lot of you are currently using safeguards for making your workstation a safer environment for your operators. 50% of people are using the DT enclosure, 25% of people are using the dual palm switches, 50% of people are using the signal tower lights, 75% of people are using an insulation mat, and 75% of people are using warning signs. So that's really good news to hear that everyone is using multiple safe workstation accessories.
Okay, so it sounds like most people have the insulation mat warning signs, right? Which they should, right? That's kind of the minimum you can do. And then it looks like 50% have gone a little bit extra and got the dual remote palm switches and the DUT enclosure. So that's good to hear. So we're kind of close to wrapping up. I'm gonna ask Bashan if there's any good questions that have come through our question widget. But till then, feel free after this webinar is completed to go on our website and look for training resources, or just review the OSHA regulations on what they feel is mandatory to provide safe workstations for anything that exceeds 50 volts. And also, it dictates that employees must be qualified to work on or near exposed energized parts. Again, they don't define what qualified means. That falls on the manufacturer. So you get to identify, well, not identify, you get to implement the training of what makes someone qualified. So it's a huge responsibility that falls on whoever's in charge of keeping everyone safe there. And then these other standards are good to reference when trying to build a safe workstation. So let me see if any questions have come through. I don't know if Bashan has anything that has come through. Let's see. So it looks like one question is asking about our interlock and what it means if it's a hardware interlock or a firmware interlock. And so that's actually a really good question. Some companies have an interlock which its purpose is to open the output relay, right? I want to turn it off. I want to turn the high voltage off. I want to turn the high current off. But it's controlled via the firmware, meaning it's software controlled, meaning as many customers I'm sure experience with us, there's a lot of firmware updates that we create because there's certain bugs or something's not behaving properly. And so once you're dependent on a software interlock or firmware controlled interlock, well, now you're just depending on software, right? Something someone's written, something that can be corrupted if it's if there's any arcing occurs internally or noise from a high voltage lead that comes close to the microprocessor and again corrupts the firmware. So you're kind of dependent on making sure that that firmware, that software doesn't fail, as opposed to Associated Research, who we have an analog hardware interlock, meaning once you pull those pins out, once that interlock is open, you know, an actual relay, the actual output relay is opened, you know, via an analog signal, via hardware, as opposed to waiting on the firmware to give you that signal to turn off your output. So that was a good question. I hope that clarifies the differences. Let me. So again, here's a link to view these resources. Hopefully that's an up-to-date link, but if not, Allison can shoot you out a link or feel free to reach out to her. Speaking of Allison, we want to congratulate her on her promotion she's received recently. And so with that, next week we will be meeting Brittany, who will be the organizer of our webinars from now on. Brittany has a great voice, so just like Allison did, so you'll look forward to hearing her call out questions and poll results. So next we want to welcome Brittany and wish her good luck next week on her first webinar. Aside from that, here's our contact information. I also want to thank our graphic designer Maggie for getting us these new slides. I don't know if anyone's watched in the past, but these are a major upgrade. They look so much nicer in the drawing. So that's the type of content we want to be bringing you this year, with some updated slides and more information that we haven't given in the past, or build upon information that we have given in the past. So again, feel free to contact Allison with any questions. Reference our website for other materials. And beyond that, Bishan will be conducting our webinar in March, but it's coming up in the next few weeks,